Application of direction, ratios to collinearity. In the study of three-dimensional geometry, one of the most fundamental tasks we encounter is determining whether a set of three given points actually lie along a single, straight line. When we find that these points are indeed positioned on the same straight line, we use a specific mathematical term for this. We say the points are collinear. In this tutorial, we are going to focus on a very efficient method to verify this. We will learn how to use the concept of direction ratios, or doctors, to mathematically prove whether or not these points are collinear. By the end of this lesson, you'll be able to apply this technique to any set of coordinates provided to you. Hello, everyone. Welcome to today's session on 3D geometry. To start things off, let's look at our first slide, which introduces the application of direction ratios to collinearity. Understanding the concept. Now that we have defined what collinearity means in our first slide, let's dive into the underlying logic. To understand how we can use direction ratios to prove collinearity, we need to rely on two fundamental geometric principles. First, we have the concept of parallelism. In three-dimensional space, we can determine if two lines are parallel by checking if their direction ratios are proportional to one another. Second, we look at the common point principle. This is the glue that connects our lines. If we have two line segments that are parallel, and we notice they share a common point, they cannot be separate parallel lines, they must actually lie on the exact same straight line. So, applying this to our topic, if we are given 3 points, A, B, and C, we can examine the line segments AB and BC. If we calculate the direction ratios for segment AB and find that they are proportional to the direction ratios of segment BC, we have proven that the segments are parallel. And because point B is a shared point between both segments, we can conclude with certainty that points A, B, and C are collinear. In the next slide, I will show you the exact step-by-step mathematical procedure to perform this check. Step-by-step procedure to check collinearity. Now that we understand the geometric logic behind why parallel lines sharing a point must be collinear, let's break down the actual mathematical procedure. If you are presented with 3 points, let's call them point A with coordinates x sub 1, y sub 1, z sub 1, point B with x sub 2, y sub 2, z sub 2, and point C with x sub 3, y sub 3, z sub 3. You can follow this 3-step process to verify their alignment. Step 1 is to find the direction ratios for the first line segment, which is AB. To do this, you simply calculate the difference between the coordinates of point B and point A specifically. You subtract x sub 1 from x sub 2, y sub 1 from y sub 2, and z sub 1 from z sub 2. To keep our work organized, let's denote these resulting values as a sub 1, b sub 1, and c sub 1. Step 2 is very similar. We need the direction ratios for the next segment, BC. Just as before, you find the difference between the coordinates of point C and point B. You'll subtract x sub 2 from x sub 3, y sub 2 from y sub 3, and z sub 2 from z sub 3. We will label these new values as a sub 2, b sub 2, and c sub 2. Finally, in step 3, we perform the test for proportionality. We need to compare the corresponding components of our two sets of ratios. The points are collinear if the ratio of a sub 1 over a sub 2 equals the ratio of b sub 1 over b sub 2, which in turn equals the ratio of c sub 1 over c sub 2, all equaling some non-zero constant, k essentially. If these fractions all result in the same number, the segments are parallel. However, if even one of these ratios is different from the others, then the points do not lie on the same line. We will apply this exact step-by-step method in the worked example coming up next. Real-world analogy. Now, before we dive into the formal calculations and the worked example in the next slide, let's take a moment to visualize what we are actually trying to achieve with a real-world analogy. Imagine a laser beam traveling through a dark room. Now, suppose you place 3 different sensors, which we will label as sensor A, sensor B, and sensor C, at different locations in that room. The sensors are considered collinear if that single, straight laser beam can pass through all three of them in one continuous, straight path. Think about the direction of that beam. If the direction from sensor A to sensor B is exactly the same, or perhaps exactly the opposite, as the direction from sensor B to sensor C, then you know for certain that all three sensors are perfectly aligned on that same path. This is exactly what we are testing mathematically when we check if the direction ratios are proportional. Worked example. Here is our problem. We need to determine if the three given points, A with coordinates 1, 2, 3, B with coordinates 3, 5, 7, and C with coordinates 5, 8, 11 are collinear. First, following the procedure we just discussed, we need to find the direction ratios for the line segment OB. To do this, we subtract the coordinates of A from B for the x component. 3 minus 1 gives us 2. For the y component, 5 minus 2 gives us 3. And for the z component, 7 minus 3 gives us 4. So our direction ratios for OB are 2, 3, 4. Next, we move to step 2, where we calculate the direction ratios for the line segment BC. Again, we subtract the coordinates of B from C looking at the x-coordinates. 5 minus 3 equals 2. For the y-coordinates, 8 minus 5 equals 3. And for the z-coordinates, 11 minus 7 equals 4. This means our direction ratios for BC are also 2, 3, 4. Now, for step 3, we must check for proportionality. We do this by comparing the ratios of the corresponding components. If we take the x components, 2 divided by 2 equals 1. Comparing the y components, 3 divided by 3 equals 1. And finally, for the z components, 4 divided by 4 equals 1. As you can see, all these ratios are equal to 1. To reach our conclusion, we can state that since the ratio of a sub 1 over a sub 2, b, sub 1 over b, sub 2, and c, sub 1 over c sub 2 all equal 1, the direction ratios are proportional. Because these segments are proportional and they share the common point b, we can confidently conclude that the points A, B, and C are indeed collinear. Now that we have understood the theory and the step-by-step procedure, let's put everything into practice with a worked example. Let's walk through the solution together. Before we move on to some important pitfalls to watch out for, notice how the direction ratios were identical in this specific case, which is a perfect example of the proportionality we've been studying. Common mistakes to avoid. First, let's talk about the subtraction order. When you are calculating your direction ratios, like when we found the values for line segment AB and then BC, try to stay consistent. For example, always subtract the first point from the second, such as B minus A, and then C minus B now. Don't panic if you accidentally do a minus B instead. Mathematically, this only changes the sign of the numbers, and since we're checking for proportionality, the constant k will simply change sign, so it won't break your final answer. However, being inconsistent, like mixing up the order between the two segments, is a recipe for confusion and unnecessary mistakes. Second, and this is a very important conceptual point, do not forget the importance of the common point. As we discussed in our Understanding the Concept slide, showing that the ratios are proportional only proves that the two line segments are parallel. Parallel lines don't necessarily touch. It is specifically because point B is shared by both segments AB and BC that we can confidently conclude the points are collinear. Without that shared point, you've only proven the lines are running in the same direction, not that they are on the same path. Finally, keep an eye out for the division by zero trap. In our proportionality formula, where we check if a 1 over a 2 equals B1 over B, 2 equals C1 over C2, you might encounter a situation where one of your components is 0, for instance, if a 2 equals 0. In mathematics, we cannot divide by 0. If this happens, don't try to force the division. Instead, simply check if the corresponding component in your first segment is also 0, meaning, check if a 1 also equals 0. If one segment has a 0 in that position and the other does not, then the ratios are not proportional, and you can immediately conclude that the points are not collinear. Now, before we wrap up our session and move on to the final summary, I want to pause and discuss some common pitfalls. Even if you understand the logic we used in our worked example, it is very easy to make small errors that can lead to the wrong conclusion. Keep these 3 points in mind, and you'll avoid the most common traps in 3D geometry. Key takeaways. First, let's revisit the definition. Remember, collinearity is simply the term we use when 3 or more points lie perfectly along a single straight line. As for the method we practiced in our worked example, the procedure is straightforward. You need to calculate the direction ratios for 2 adjacent segments. For instance, if you are given points A, B, and C, you should find the direction ratios for the segment OB and then for the segment BC. Now, what is the specific condition we are looking for? The points are collinear if the direction ratios of OB are proportional to the direction ratios of BC. In mathematical terms, this means the direction ratios of OB are equal to a constant, let's call it K, multiplied by the direction ratios of BC. Finally, let's summarize the underlying logic that makes this whole technique work. When we find that the direction ratios are proportional, it tells us that the 2 line segments are parallel. However, as we discussed in our earlier slides, parallelism alone isn't enough. It is the fact that these segments share a common point, in our case, point B, that completes the logic, proving that the points are indeed collinear. All right, we have reached the end of our tutorial. Let's take a moment to recap everything we have covered today so you can consolidate your understanding. I hope this summary helps clarify the concept. Keep practicing these steps, and you'll be able to tackle these 3D geometry problems with confidence.